I'm thinking of giving an exam. The third exam during they call it dead week, the last week before your final exam. Will that be okay with you guys? Okay, so I will give it to you on. So I will decide either give it to you on Wednesday. I think I'll give it to you on Wednesday. Yeah. So I will update the syllabus. And then the final exam, I think it's in the morning. Our final exam is in the morning. It's not in the afternoon. So I will also check.
So will we be taking exam 3 in the morning like normal in class?
The final exam, right?
No, that's our exam.
Yes.
Okay.
Just in class. Okay, let's continue from where we left. We were proving whether this linear transformation, whether this transformation is a matrix, is actually a linear transformation. So we can let A, B be elements of we are here. Then we said that for the linear transformation, then the transformation T of now, if we let A and B to be in Mn, then C multiplied by A plus D multiplied by B is the same as. So what will it give us? So it will give us CA plus DB, just like this one over here, minus CA plus DB transform. So just the way it is here. But the issue is we just want to check whether this is linear transformation by using our definition that we did. Then when you open this bracket, then this is CA plus DB minus the transform. If we remember how we were using the transpose, then we can distribute this transpose here, CA transpose plus DB minus here, DB transpose. Then if we now collect the A's and B's and put them together, then this is the same as CA minus CA transpose plus DB minus DB transpose. Okay. Then we can factor out our C here. So we get C and then A minus A transpose plus factor out D, B minus B transpose here. Then what was A minus A transpose? A minus A transpose is T of A here. So it is the same as C, T of A, and then this is similar to this, so plus D, T of B. So then it shows that these can be distributed like this. So therefore, so T is a linear transformation from Mn by n to itself. So that's how we prove the transformation. Okay, let's look at this theorem here, theorem 1.3. if we let V and W be vector spaces and denotes the zero vector of V and W by 0V, and these are vectors, and 0W, 0V and 0W respectively. Then if T from V to W is a linear transformation, if T from V to W is a linear transformation, then T of zero vector is equals to 0W. T of zero vector. So if zero vector is this, then 0W is it. Then the transformation of zero vector is also equals to 0 vector, which is 2. So that is how that is. So it is easy to prove this. So you just say, so you can just take T of zero vector is similar to T of 0 and then 0 vector, which is the same as factoring out 0, 0 T of 0 vector. And this is giving us 0 of 0 W, which is the same as 0 W. So just simple. So it shows that that's a linear transformation. Linear transformation. Okay, let's look at another example. Example number 2 in this section. Is the transformation T from the polynomial with real coefficients to real number defined by TP equals to P naught plus 1 for P elements of Pn and linear transformation. Is this a linear transformation? So we need to check whether that will give us a linear transformation. So how can we check this is a linear transformation? So we can start by using the subspace test. So we can prove this. So we can say the 0 vector, which is 0 of Pn, is the 0 polynomial, where it gives us 0 of x equal to 0 plus 0x plus 0x square plus 0xn minus 1 plus 0xn. Okay. So the zero vector will give us that. So it means the 0 vector of x will actually give us a 0. So it is equals to 0. So it is equals to 0. Now since t of 0, now if we put a 0 here, as a 0 in this p here, then it should give us 0 of 0 plus 1. So we've seen that 0 here will give us 0. So if we now put a 0 here, then it should be 0 where there is p of 0 plus 1, which will give us what? Which will give us 0 plus 1, since this one is 0, which we got here. Now, this 0 plus 1 is the same as 1, and this is not equals to what? That is not equals to 0. So it is not equals to 0. So therefore, this is not a linear transformation, since it is not giving us what? It is not giving us 0. So T is not a linear transformation. T is not a linear transformation. Okay. Any question after that? Okay, let's look at the next section, which is section number 2. And we have looked at this, the range and kernel of a linear. We have actually seen this one in the previous section. So let's see how we can get the range kernel of a linear transformation. So let's start by definition 2.1. And we already defined this one last time. So we said, if we let T to be from V to W, be a linear transformation. Then number 1, the range of T is image of T. The range of T is the image of T, which is equals to T of U, where U is in V. T of U, where U is in V. So if we have this transformation from V to this one, then the image is in what? In W. And that image is actually T of U. So we have this here, another one here. So if you have our V here, U here, which is an element of V, then our transformation will be here, which is T of U. So it transforms from here to here. So the image here of U is actually T of U, which is here. So that is the image. That is the image. Then number 2, the kernel of T is the car of T, which is equals to U, which is an element of V, such that T of U is equals to 0. T of U is equals to 0. So the kernel is the 0. The 0. Right. So it is 0. So the solution that you should be the 0. So basically the kernel, we will see that the range, we saw this one last time, but the range was the what? The column space. And the kernel was the what? The null space, because we're getting the solution. The solution to be equals to 0. The solution to be equals to 0. Okay, let's see another theorem here, which you can check it in your textbook for the proof. If we let T to be from V to W be a linear transformation, then number one, the range of T is a subspace of W. And number two, the kernel of T is a subspace of V. It's a subspace of V. So you go and look at the textbook. So the range of T is actually in that, and the range of T is the image, which is the image of T, which are in one. And the kernel are in V. The kernel are in V. So here you use the subspace test. Use the subspace test. So you start by starting by checking the 0 in W and also the 0 in the corner. Okay, let's look at the first example here. Example number 3. Example number 3. Describe the range and kernel of each linear transformations T. Describe the range and the kernel of each linear transformation T. So let's start from the first one here. Number A. If we let A be an n by n matrix with real entries, and the transformation will be from Rn to Rm, be the linear. Be the linear transformation defined by T of x equals to Ax for x element of Rn and n. So if you have this transformation through the matrix, Rn to Rm. Now let's check. Let's describe the range and the kernel of this. So what is the range and the kernel there? So the range is the image in what? In of T, which is in, and the kernel is there. So then the solution. So if we remember, I think we actually defined this one last time, but we can repeat it here. So we were writing A to be the vectors. So the matrix A are the vectors which you combine A1, A2, all the way to AN. So that is the matrix A. So you bring together the vectors. So it forms the matrix A. Where A1 all the way to AN are in Rm. So those are in Rm. So they are in Rm. Then the image of T, the image of T is actually the same as T of X, where X equals to X1, X2, all the way to Xn, where these X are in what? These X are in Rn, where these X are in Rn. So T of X, so you can let X to be Rn, and T of X, so that our image will be T of X equals 1. So if we recall, then this T of X is the same as A of X. Yeah, it's the same as A of X, whereby X is equals to X1, X2. These are the weights up to Xn, and these are in Rn. These are Rn. That is how we were writing that. So T of X is that. Then this is the same as if we write this as a linear combination. So this is the same as X1 A1 plus X2 A2 plus Xn AN as a linear combination. Say that X1, X2 are actually the solutions X3, Xn, and these are in real numbers. So those are real numbers. So those are the solutions that we get from this. Then therefore, if these are the solutions X1, X2, Xn, then therefore this is equals to the span of the vectors A1, A2, all the way to AN. All the way to AN. And this span, if we remember, the span is now equals to what? Is the column space of A. Span is the column space. So if these are giving us a solution, then we can get that this one as the span. So the span is a linear combination. So therefore, the image of T is the same as the column space of A. For the nose, for the other one, the kernel of T is equals to X, which are in Rn, such that T of X equals to what? Equals to 0, and this 0 is in Rm. This 0 is in Rm. Then this is actually the same as X, which is in Rn, such that Ax is equals to 0, which is in Rm. 0, which is in Rm. So it is the same as Ax equals to 0, which is in Rm. Therefore, this is equals to the null space of A. The null space of A. So if we remember, that is the column, the solution of that is okay. Any question after that? So that one is the image or the range and the color of the matrix. Example number B. Example number B. if we let T from R2 to R4 be the linear transformation defined by T of X equals to AX for X elements of R2, where A equals to 2, -1, -4, 3, -6, 3, 12, and -9. Then describe the range and the kernel of it. Describe the range and the kernel. Describe the range and the kernel. So how can we get the first one, which is the image of that? So let's look at the solution here. Now, we can take A1 and A2. So we can take A1, the vector A1 to be equals to 2, -1, -4, and 3. And the vector A2 to be equals to -6, 3, 12, and -9. Actually, you can still write the vectors. Okay. So you can either write, what do you call this, parentheses? You can use the parentheses to be on one line, or you can use brackets, right? To be the column. So you can either still write this one as A1 to be equals to 2, -1, -4, and 3. It is still the same thing with up. So if we have those ones as the vectors, then we can see that this A1 and A2, they have some common value there. They have some common value here. So we can see that A1 is equals to -2 A1. No, -2 A1 is equals to H, right? -2 A1 is equals to H. Oh, -3, sorry. -3. -3 A1 is equals to H. Then, therefore, the image there, the image, which is the span, is, so the image of T is equals to, if we can recall, is equals to the span of A1 and what? And A2. It's equals to the span of A1 and A2. Now, since this is a factor of the other, then therefore the image can be equals to the span of A1. You can just take one, which is the same as what? The span of, you can put it like -2, -1, -4, and 3. So that is image. Now, what is the kernel? So what is the kernel? So to get a kernel of T, then the kernel of T is equals to, if we take all these to be A1 and A2 and all that, then is equals to the solution of what? x, which is in, if we can take x to be in R2, yeah, if we can take x to be in R2, such that the solution of AX equals to what? Equals to 0, and that 0 is in what? In R4. That's 0 is in R4. So it is a solution. Then we need to get a solution. So to get a solution here, then we now write, so it is basically the same as A, if we have that AX equals to 0, AX equals to 0. Then we now write the augmented matrix of this, which is equals to 2, -6, and then 0, -1, 3, 0, -4, 12, 0, 3, -9, and 0. And then we do what? That we reduce it completely. Then we reduce it completely. Now, once we reduce this, so we reduce that completely. So we need to make this 0, 0, 0, and the rest. So what you should get is, first of all, you need to transform this one to 1. So you can say R1 to be 1 over 2 R1, which should give us 1, and then -3, 0, -1, 3, 0, -4, 12, 0, and then 3, -9, 0. Then we now reduce the rest. So to reduce the rest, then to get the new R2, then it is R2 plus R1. To get the new R3, then R3 plus 4R1. And then to get the new R4, then R4 minus 3R1. So finally, what you should get is 1, -3, 0, and then all the rest are zeros. All the rest are zeros. So therefore, our new linear equation there will now be x1 minus 3x2 equals to 0. So basically, we have our basic variable as x1 and our free variable as x2, x1, and x2. So then x1 equals to 3x2, x1 equals to 3x2. Now our solution set, the solution set, which is x, is equals to x1, x2, and this is equals to x1 is 3x2, and then our free variable, which is x2, right? Is x2, and therefore we can factor out x2 there, so x2, and this is equals to 3 and then 1. So then our null space of A is equals to the span of this vector here, which is what? 3 and 1. Just 3 and 1. So actually it's similar to what we did previously. Any question after that? Okay, let's look at another example. Let's see. If we let the transformation from the polynomial with real coefficients to Rn, to real number, Rn, be the linear transformation, which is defined by T of A naught plus A1x plus ANXN, which will give us A1 up to AN for A naught, A1 up to AN, and these are in real numbers. So real numbers. Then describe the range and the kernel. So look at this, the transformation. T of A or all these are in what? Is a polynomial. So this one is a polynomial. So this polynomial here is giving us A1. So it is actually, if we take the transformation here, then this T of A naught will be 0. So it is constant. Right? So T of this will now be equals to that. Now let's check the range and the kernel. So let's look at the range and the kernel. So let's start from the range. So the solution. So the range is the same as image of T, the image of T. And the image of T is equals to T of A naught plus A1x plus A NXN, such that A naught, A1 all the way to AN are in R. Then this is giving us A1, A2, all the way to AN, such that A1, A2, all the way to AN are elements of real number. So this one is giving us that. Then this is, so this is basically in what? So this is in, it is in R. So that is in R. So the image is A1 is in R. It is in R. So then if we let the polynomial P of X to be equals to A naught plus A1x plus ANXN be in Pn, where A naught, A1, all the way to AN elements of real number, then P of X is an element of kernel of what? It's an element of kernel of T. P of X is an element in kernel of T. So this is a polynomial which is here, which is in P of N. Then if this is the kernel, so therefore T of A naught plus a1x plus anxn is equals to what? Should give us 0, 0, all the way to zeros. So they should give us 0. So the kernel is equals to 0. So then, since this is the transformation, so then this should be equals to a1, a2, all the way to an, and all this should be equals to what? 0, 0, 0, 0, all the way zeros there. So this t is equals to this. So t, like what we've done here, is equals to a1, but this a1 up to an is equals to zeros. So therefore, then a1 equals to 0, a2 equals to 0, all the way to an equals to 1, 0, equals to 0. So then the kernel of t is equals to a naught plus a1x plus an xn, such that a naught is in R and a1 all the way equals to 0, equals to a equals to an, which is equals to a naught, and this a naught is a real number. So then the kernel, so the kernel of T is the set of all constant polynomials. So we know that the kernel of T is equal to the transformation. And we say that the transformation is equal to a1, a2, a2, and these are equal to 0, 0, 0. So therefore, a1 up to an are zeros. But the one which is not equal to 0 is the one is a constant. All these are zeros. So therefore, the kernel is a set of all constant. Okay, let's look at another example. Example number B. Let the transformation T from M 2/2 to M 2/2 be the linear transformation defined by T of A equals to A minus A transpose for A element of M 2/2. Now describe the kernel, and the range of that. So if this is a 2/2, if this is a 2/2 matrix, so what is the kernel and the range? So what is the kernel and the range? Now, solution. If we can take so since we have seen that T of A to be equals to A minus AT. Yeah. Then we can let C to be equals to A minus A transpose. And this C is the image. So this C, so we can let, and C is im of T. So that's C to be the image of T. So we can find some A, which is in M 2 by 2, such that T of A equals to what? Equals to C. Such that T of A equals to C, since we have let C to be A minus A transpose. So now C transpose, if we transpose now this C transpose is the same as A minus A transpose, and then we do what? We transpose. So, and this is equals to A transpose minus A transpose, which is equals to A transpose minus what? A. And this is the same as what? Minus A minus A transpose. Minus A minus A transpose. Right? So then this is the same as what? This is the same as minus C. As we can see, it is the same as minus C. Same as minus C. So it's the same as minus C. Now then, if C satisfies C transpose, which is equal to minus C, then take A to be equals to 1 over 2C. And this should be in M2 by 2. Then T of A equals to A minus A transpose, which is the same as 1 all over 2 C minus 1 all over 2 C transpose. 1 all over 2 minus 1 all over 2 C transpose, which is the same as 1 all over 2 C minus 1 all over 2 C transpose, which is the same as 1 over 2 C minus 1 over 2 minus C. Okay. And this is equals to 1 over 2C plus 1 over 2C, which is equals to C. And this C is an element of image of T. Now, here, if we take A to be equals to 1 all over 2C, take A to be equals to 1 over 2C. Where there is A, you put 1 over 2C. Then if we substitute like this, then 1 over 2C minus 1 over 2C transpose is the same as minus C, like what we've just gotten here. Then therefore, if we do the algebra here, then we find that 1 over 2C equals to actually C. And we say this C is what? We say this C is A minus A transpose. So therefore, our C is the what? Is the image of T. Our C is the image of T. Okay, we can continue from there on Friday. When we meet on Friday, we will look at the kernel of T. Now, how will we get the kernel? I'll post the notes in the voice.
I was really for focus out to like, preparation for the next like my schedule doesn't match.
Okay, you can email me when you're ready.
Okay.
Okay.
Like each day is kind of okay on during the week.
Yeah. So anytime you're free, let me know.
Okay.
Just email me when you're free, and then I'll see my time